Right, last but certainly not least, we will have Chase Hancock joining us. So Chase is the portfolio manager at Uptapped, and he's going to be discussing energy and nutrient humps with us. In terms of fun facts, pretty short and sweet, he's left-handed. Thanks, Chase.
All right. Tēnā koutou katoa. Jeffrey, how much time do I have? 45 minutes? No, it's 20 minutes. We'll fit inside of that. I was going to start by jumping right in, but I actually realized that all the speakers before have actually set a really good foundation for this presentation. So a few things to recognize. Ben from Claris, it's the importance of the agricultural sector contribution and the critical aspect of aggregation in the bioenergy space. Sean, the necessity of certification for biomethane. Elzbieta, the criticality of feedstock supply and, well, gate fees. And James, renewable gas to grid, you're actually doing it so we can, so we have something to talk about. So with that, I will jump in. So if you haven't heard Uptapted's tagline before, we're focused on advancing New Zealand's future energy sector by accelerating the demonstration, commercialization, and deployment of innovative and emerging technologies into the market. In short, we spend most of our efforts in enhancing and enabling pathways to the future in the present. One of the most impactful ways to do this is to connect communities to technology. Today, we'll start by focusing on the problems with AD at an individual farming level and move to a combination of a concept and a technology that can provide a solution. So, I am, like was previously mentioned, I'm the portfolio manager, and today we'll focus on these concepts and learnings from the Energy and Nutrient Hub feasibility study. This is a study that connects the farming sector with the technology that can unlock the nexus between waste, energy, and nutrients. There we go. Got through that one already. Okay, so we'll jump right into the problem. So some of these themes have been mentioned before. I guess AD often doesn't work at a typical farming level. Economies of scale are central to this topic, and as Elzbieta has mentioned, the quantity, quality, and seasonality of on-farm manures at a typical New Zealand farm are insufficient to generate adequate biogas for the capital cost required. In particular, pasture-based farming management practices mean an average of 7% of the manure production is captured. We could argue about that number, but it's low no matter what. You can see that on the graph there. We sit at the bottom left-hand corner. So this is typically through effluent ponds, wash down, and scraping at the milk shed. Both of these aspects challenge the technical and commercial viability of the European AD model. Then we can move straight to biogas prices. This has already been mentioned as well, but the available feed-in gas prices in New Zealand are significantly lower than Europe, making upgrading a less compelling option. Unless the levelized cost of energy is significantly lower than the energy price, the profitability of the process could not stand alone on energy production. Across the current range of methane prices, which you could say $20 to $30 a gigajoule, the farms would require additional sources of revenue from the AD process. So you can see that on the figure on the right. Then we'll move to the third and fourth, which is the high capital and operating cost versus performance. So for a farm and farming cluster, simply dealing with manure as feedstock, it's likely to have sufficient land to manage its manure-based digestate, but insufficient energy generation potential to reach viable scale. For the purposes of this study, we considered 50,000 gigajoules per annum as that viable scale. That leads to the fact that physical integration of the relatively poor quality on-farm manures offer potential risks to performance and require larger AD tank system to accommodate these high volume, low concentration feedstocks. As a result, the operability and capital costs may be too high. The figure on the left highlights the challenges of plant sizing relative to feedstocks. As you can see, The arrow on the y-axis of the graph, the bottom left-hand blue one, represents the manure at the single farm level alone, which is nowhere near the viability line. This same figure also highlights challenges of nutrient management. So New Zealand pasture-based farming system mean that there is significant risk associated with the nutrient capacity from AD processing. Moreover, discussions with the case study with farming managers clearly highlighted that digestate management is considered a very high barrier to adoption due to the risks to irrigation systems, i.e. presence of solids and other things that may cause issues within sprinkler heads and other irrigation components. And the low nutrient concentrations in high volume liquids would require more capital investment in irrigation equipment to distribute across more land. So now that we've covered the basics on the problem, let's jump to the solution. So in this study, we considered what we call the energy and nutrient hub concept. This system is envisioned as a hybrid combination of two digestion processes. So on the top, the larger square is the low intensity digestion in a earth basin digester, which is designed to take the majority of the low strength feeds, i.e. on-farm manures, and then to the high intensity digestion via a above ground tank digester, taking the majority of the imported higher strength feeds, shown on the bottom there. The dual system benefits from the combination of high loading capacity of the tank digester, capable of dealing with high solids inputs and high yielding substrates, and it's coupled with the hydraulic and load buffering capacity of the earth basin digester. The linkage between the digestion processes is a technology under development by an innovator, Ara Ake, supporting ketogenics. The energy and nutrient hub enables two main benefits, which I'll cover in the next two slides, both of which can be further augmented by ketogenics CetoBoost technology. Right. So, the first is the resilience and economies of scale. Using an imported feedstock model, which is allowed by having a hub model, means the inherent seasonality of the on-farm feedstocks is addressed through careful consideration of available inputs according to their relative availability. From the hub perspective, locations with ready access to a range of suitable feedstocks will be desirable. Furthermore, success will obviously be based on well-developed relationships with feedstock providers. This actually provides an opportunity for broader choice in site selection, rather than simply accepting the home farm location for 100% of the manure-based system. You can see here this figure illustrates the difference in feedstocks between seasonality by color, right? So you notice that August through November are radically different than January through April, for example. The second and related benefit is a configuration to enable high and low quality feedstock. The hub can be sized at or above the economic scale of 50,000 gigajoules per annum and accommodate feedstocks with differing relative contributions. You can see in that left-hand column that there is quite a difference between these if this is not a space you're familiar with. And so although poorer quality feedstocks tend to pose difficulties in digestion, they tend to attract higher disposal gate fees, like paunch, pulp, or paper residues, and can be considered rather than heavily relying on performance biogas materials such as maize straw, which will likely need to be purchased. So that brings us to the linkage between the two. The enabler, which is CetoBoost technology. It's a hydrothermal oxidation technology, which is just a combination of heat, pressure, and air tuned for the particular environment it's deployed in to deal with anaerobic digestate, and it offers a novel solution to many of these challenges. CetoBoost breaks down organic materials to more bioavailable components, significantly enhancing methane production rates, efficiency, particularly from difficult to digest substrates, while also helping streamline management and logistics of digestate. The potential for CetoBoost to improve gas productivity and nutrient recycling while accommodating lower quality feedstock can therefore be a component of a viable larger scale anaerobic digestion system. So there are some key benefits. We'll just run through real quick. It's got a relatively small footprint. It's modular, containerized, scalable system. We're seeing increased gas yields through digestate processing, diminished digestate volumes for easier logistics. It enables processing for higher value, hard to process waste, which opens the door for higher gate fee potential. There's a potential for higher value digestate products such as ammonia salts and phosphate. And then lastly, it is an exothermic process, so there's a potential for it to provide heat to the mesothermic digester, which is that above ground tank. With that in mind, we'll look at some of the high level conclusions for the study. So I guess in summary, it's fair to say the energy and nutrient hub concept is likely necessary to achieve the economic viability, and the Cedo Boost technology adds significant value by enhancing energy production and digestate management. There are some high-level takeaways. I guess the main takeaway from an economic point of view is that both the hub as a standalone AD concept and with the Cedo Boost technology anticipate payback near the 5-year mark. We saw positive outcomes for all the applied commercial metrics, IRR, ROI, and simple payback that I just discussed. The modeling showed a 19% increase in gas production, which would bring the 65,000 gigajoule a year plant up to 78,000. And then greater nutrient value is realizable through downstream processing of digestate. And then using the levelized, I guess another key fact, this is something that has actually been mentioned several times, is that the cost of energy production of biogas is predicted to be $35 per gigajoule, which is significantly higher than the applied methane price right now. So that's not a surprise. And what that means in practice is that profitability of this concept will rely on other sources of income, i.e. gate fees, and just some way of capturing value for the discharge materials. And in a rural setting, exactly how that works is not quite clear yet. So I guess the revenue from these sources in terms of how it was modeled in the study is that it's roughly the magnitude of the revenue from the gas and from the other sources is roughly 50-50 split. All right. I think I'm about ready to close and open for questions. But first, I want to say, an outcome like this is the result of contributions by many. The first person to thank would be Jeffrey from GasNZ for taking an interest in this project while it's still under development. I hope it shows value for the community's work you're doing now. I'd like to thank Cetogenics and Cedo Boost Technology. I'd like to thank Stefan Heubeck and BPO for a feasibility study that can only be described as a labor of love. And last but not least, I'd like to thank the small and passionate team at Araki. I hope this talk has been useful to show this pathway to future energy as promised. Thank you all for listening, and I'd like to open up the floor to questions.
Thanks, Chase. Very interesting. We've got one here on the Slido. In terms of in real world terms, what would one of these energy nutrient hubs look like? How big? What kind of area would the feedstocks come from?
All right. Yeah. So I guess without being able to answer those numerically, I think the way transport costs are a key factor, obviously, in anything bioenergy. And this has been designed to minimize those to an economical distance. The study itself took a look at 3 different clusters of farms that were all located near an industrial organic waste producer and pipeline access. So in the case of this, the transport is actually pretty narrow, and that's what many of the results are from our leading cluster farm. Does that answer the question? I'm not sure it fully does, but
probably.
Yeah.
I've got one of my own. So on your last slide there, you mentioned a pilot, or I'm just quite intrigued.
Yep.
What's kind of next steps off the back of this feasibility and modelling piece?
Yep. So we co-funded the feasibility study with the intent of opening the door for a pilot. I guess we and the other farming partners see real potential for a pilot based on these economic outcomes, so that we will be looking to take that next step.
Cool. So you're after some partners in that space?
We have partners for this, but if there are any other people interested, I think, you're thinking about 65,000 gigajoules per annum versus the 180 petajoules. Like, we could kind of use hundreds of these. So if anyone's interested, let's talk.
Fantastic. Thanks, Chase. Is there any other questions from the floor? No. Well, thanks very much, Chase.